So now that we've had a chance to talk about the monitor object pattern qua pattern, right? We talked about its intent and its structure and functionality and known uses and so on. It's time to turn our attention to a very detailed walkthrough of the application of this pattern in the context of the Java LInkedBlockingQueue class. And we're going to see how this is applied in LInkedBlockingQueue, which is available in Java util concurrent, just in the Java platform. And of course, it's also available in the Android platform in basically the same place. And it's basically the same implementation for that matter. So let's go ahead and talk about how to implement LInkedBlockingQueue. So as a recap, LInkedBlockingQueue is essentially a blocking queue. It's a bounded blocking queue. You can give it a maximum size. You can give it a very large maximum size, but it has a maximum size. And as the name suggests, it's based on linked nodes that will queue the elements that are put in the queue in, first out order. So the order that they're put into the queue will be the same order that they're taken out of the queue. So let's talk about some of the implementation steps that are involved in implementing this. And to see more about this particular discussion, take a look at the Pattern-Oriented Software Architecture Volume 2 book, which talks about how to implement bounded queue. It doesn't talk about it in Java, but it talks about it in the context of C++, but it's still quite relevant, same pattern. Okay, so the first thing you do when you're implementing this pattern, you should figure out what are your interface methods that you want to be synchronized. So these are the ones that are going to have that property that only one thread at a time can be calling these methods and having them actually do anything. Otherwise, they're going to be queued up waiting on the monitor lock or monitor locks in order to ensure that we don't end up with corruption of the internal state, the internal mutable shared state. And in this case, we're going to have put and take be the interface methods. That's what we're defining to the outside world. Then the next thing you have to do is implement or define the implementation methods. These are the ones that are going to implement the actual logic to do the put and take. And you'll see when we get a little further into this that this can be done in a very clever way to kind of factor out code that's related to the logic of the queue versus the synchronization of the queue. Although the particular implementation we'll look at with Java mixes them up just a tiny bit. Then the next thing you need to do is define the internal state and of course the synchronization and scheduling mechanisms. So in the context of LInkedBlockingQueue, these would be things like a head and last field that are nodes. We'll take a look at what a node is in a minute. We have an atomic integer that keeps track of the number of elements. We have a capacity, which is what's the max number of nodes that can be in the queue before it's considered full. And then we have a full battery of reentrant locks and condition objects. We have one reentrant lock that manages taking or removing or trying to remove, another reentrant lock that's used to manage putting or attempting to put into a full queue. And then we have a pair of condition objects for not empty and not full conditions. And then after you've kind of figured out sort of the schema of all this stuff, the implementation artifacts and fields, then you have to implement all the methods and all the data method members and fields and so on. So let's start with the interface and implementation methods. So these, of course, are the ones that are synchronized. That is the interface that's going to be seen by the outside world. And they need to be synchronized either in virtue of using the synchronized keyword, which has all the downsides we've talked about, or by using something like reentrant lock. So let's take a look and see how this is going to work in the context of LInkedBlockingQueue. As you can see, for LInkedBlockingQueue, this is going to inherit the blocking queue interface, which is a pretty large interface if you take a look at it. So I'm not going to spend a lot of time going through all the methods in blocking queue or LInkedBlockingQueue for that matter, but be aware that the key ones we really care about here are put and take, and they do the obvious thing. Put's going to attempt to put an item in the queue, blocking until it's not full, if it's full, and take is going to try to remove something from the queue, blocking until it's not empty, if it's empty. And you can read more about that at the links at the bottom of the slide. Okay, so put and take, and under the hood, of course, they're going to be adding and removing things from the linked list that's used to actually store the various elements that constitute the LInkedBlockingQueue's content. Now let's take a look at the implementation methods. These are private, or protected. You can see this is a UML notation, so public methods are designated by putting a plus sign in front, and methods that are private are designated by putting a minus sign in front, just UML syntax. So these are the things you don't see at the interface level unless you read the code, but they're there under the hood, and that's what we care about here. Now, the actual way that the code is structured is by using something called the thread-safe interface pattern. And that's another pattern that appears in the POSA 2 book. So you kind of get multiple patterns here for the price of one. We get the monitor object pattern, which is the main pattern we're focusing on, but we're going to see the implementation will also leverage other patterns like thread-safe interface, like scope locking, and so on and so forth. And that's worth being aware of because it just demonstrates the fundamental social and gregarious nature of patterns. Patterns like to hang out. They like to do things together. They like to get together in groups and solve problems collectively. You can take a look at this link to find out more information about the locking patterns that are used here, or you can read the POSA 2 book, either one. The two methods we're going to look at are enqueue and dequeue. This again is the Java implementation that we're looking at. Enqueue will link a node at the end of the queue, so it enqueues it in FIFO order, and dequeue will remove a node from the head of the queue, so it removes it or dequeues it in FIFO order. Now, what's interesting about this, and this is where the thread-safe interface pattern comes into play, the put and take method are the ones that will acquire and release the monitor locks. So enqueue and dequeue are called assuming locks are held, so they don't have to themselves have any locking behavior. They do a few synchronization related things related to coordination, but they don't deal with locking. So let's go ahead and take a look at the internal state and synchronization and scheduling mechanisms. And of course, the whole point of this is to ensure that our implementation of a monitor object in general, or the link blocking queue in particular, does not incur race conditions. So here's kind of what it looks like. We're going to use a monitor lock to ensure we don't have race conditions, and we'll use monitor condition or monitor conditions in order to ensure that we're able to coordinate things properly. All right, so you already know what these things do. The monitor condition can be used to suspend and resume something, waiting for the condition to occur to its liking, and it will then also be used to notify things that something has changed that may be to their liking, so they can go ahead and potentially make forward progress. The monitor lock must be held as long as some invariants are not satisfied. That's just a fancy way of saying don't let multiple threads see the internal state of your monitor object or your link blocking queue until everything is back to the consistent order that we want it to be in when we're done doing a put or a take. You can read more about invariants by taking a look at the link at the bottom of the slide. So the invariants must hold when a synchronization or a synchronized method waits on a monitor condition. So by the time it gets to that point, everything has to be in a consistent state. And then they also likewise must hold before processing resumes after the monitor condition is notified. These are sort of obvious things once you understand the pattern, but when you're first trying to figure this stuff out, getting your head around invariants is important. It's important for any kind of programming. It's particularly important for concurrent programming, because if you're not careful, you can end up with invariants being exposed and compromised when locks are not held. So here's what the actual state looks like internally to the link blocking queue. You can see here that we have head and last, and those are nodes. And you can see that a node is basically a nested class that contains an item, which is the content that you're putting in or taking from the queue. And then it also contains a next field, and the next field is used to link it together. And you can see here that this particular implementation has the link blocking queue be done in a singly linked model. And that's because it's managed in FIFO order. Okay, we also keep track of the capacity, which is the max number of nodes that can be in queue at any one point before the queue is considered full. And then there's also an atomic integer that's used to keep track of the number of elements. And you'll see it's used in a very, very clever way in order to try to reduce the scope over which we have to acquire the reentrant locks. So just trying to make the locking as lightweight and as optimized as possible. And that is implemented as an atomic integer. Then we also have the various fields that relate to synchronization. And as you can see here, these are all things that come straight out of the Java util concurrent package, and they include not empty and not full conditions to manage putting and taking, and then a take lock and a put lock. The take lock and put lock being split is what makes this particular implementation so interesting and so clever. If you want to learn more about the implementation of a linked blocking queue that is optimized to allow parallel in-queue and D-queue, take a look at this paper down here that was published some, 25 years ago, I guess at this point, that talks more about how this all works. So let's talk about how we'd implement all this stuff. This is where we finally get down to the point where we're gonna do the code. So linked blocking queue has the take and put method. And let's take a look at that. So first thing we do before we can do any of the take and put method implementation is we have to initialize all the fields, all the data members. And as you can see here, we're going to do this by having separate reentrant locks for the take lock and the put lock, and then separate conditions for the full or the not full and not empty conditions. And then we also have to implement our count to start out at 0. Here's the constructor. You can see what it does is it goes ahead and does a little sanity check to make sure that capacity is properly defined. We don't want a negative capacity. This is made more complicated by the fact that Java does not support unsigned integers. And then we set the capacity field to whatever's passed in as a parameter. And then we initialize the last and head fields to both point to a common node. So this is an example that has a dummy node to simplify inserts and removals, or NQs and DQs. The actual implementation of the put and take methods uses that thread safe interface pattern I talked about before that you could read about here at this link or in the POSIT 2 book. The put and take methods also apply the guarded suspension pattern. We've talked about this before in the context of condition objects, and it's going to be applied here all over the place. So let's take a look at put. Put is going to insert the parameter E into the queue, waiting, if necessary, for space to become available. And here's what it looks like. So we come in here, we allocate a new node that's going to hold the element. We then go ahead and put the put lock into a local variable called put lock. We go ahead and get the atomic integer, and we store that into a local variable as well. And then we go ahead and we acquire the lock interruptibly. So we can be interrupted, which is another nice property we get over using synchronized methods or synchronized statements in Java. So at that point, we're going to block until we have exclusive access to the rest of this critical section. Once we've got exclusive access, we then come in and use a try finally block. You'll see the rest of that in a second. And while the queue is empty, this is put, while the queue is full, while get equals capacity, this is a call on the atomic integer count. So this is an atomic call. So while the capacity is full, we're going to go and block ourselves on the not full await method. So that's going to go ahead and release the lock. In this case, this is the put lock, and then we're going to go to sleep. At some point, someone will remove something, conceivably, from the queue, and then not full will be signaled. We'll wake up. Let's assume, for sake of argument, that the capacity is no longer full, so that condition fails, so we drop out of the while loop. Then we can go ahead and enqueue the element, the node, into the queue. And here's what that looks like. You can see it's super simple. It just goes ahead and takes the node and links it in at the end of the linked list. So it just sticks it at the end. This is why we use a dummy node. It makes this kind of thing very simple because there's no null case to have to be concerned with. Notice how enqueue is only called when the lock is held. So that's the thread safe interface pattern we talked about before. Here's the rest of the logic for put. We then go ahead and increment the count by 1. And if the value we got back +1 is less than the capacity, because we just added a new element. So in other words, if the queue is not full, we're then going to go ahead and signal that we are not full. And that allows anybody who's waiting that they can also go ahead and try to do a put as well. And then the final thing we do, we always use a try finally block here. We unlock the put lock. This, of course, uses the scope locking pattern that we talked about before. And then the last thing we do here is if the count equals 0, in other words, we've reached a point where there's going to be, we've taken something out of the queue and there's nothing there, we're going to go ahead and signal that it's not empty. And here's what signal not empty does. You can see signal not empty, which is a method call that's invoked from put and shared between various things, which is why it's factored out into its own call. It acquires the take lock. And once the take lock is held, it signals the not empty condition. And then, and then it releases that take lock. So again, it uses the try finally block, like we've gotten in the habit of doing, hopefully, and it will signal any other waiting threads that are waiting for the queue to be not empty. Because remember, again, we just put something into the queue. So if the queue had been, if it had been not empty, if somebody was waiting and the queue had been empty and we just put something in it, then we go ahead and signal them and say, you can make forward progress at this point. Let's now go ahead and take a look at the take method. This is the other side of the coin, if you will. It tries to retrieve and remove an element from the head of the queue, waiting, if necessary, until the element becomes available. And its implementation is structured in a very similar way, although the logic, of course, is slightly different. So it comes in here, acquires the take lock. Remember, where it's the put method acquired the put lock. It acquires the take lock, and then it's going to use the atomic integer to wait while the queue is empty. So if the number of elements are 0, it's going to await on the not empty condition, because it's going to basically go to sleep till not full, put something in there. Once it finally gets through that guarded suspension portion, it's going to go ahead and dequeue the first item and get it back. And then what it's going to do is it'll unlock the lock in the try finally block and then return that particular value that it dequeued. So that's basically how this works. And you can see that this is what it looks like in Android. You can use the same type of thing. And Android actually has monitor objects in various places. I won't go through this in detail because I think we're starting to run out of time. But basically, if you take a look at the Android source code, you'll also see that it uses the monitor object pattern in other places besides just in the context of the implementation of the linked blocking queue. And in particular, the calendar application is going to use the monitor object as well. So I'll put these slides out here. You can see that, as you can see here, it's using linked blocking queue in order to implement the logic that's in the calendar application. But again, I think we're starting to run a little bit short of time, so I'm going to just kind of skip through this stuff. So to wrap up our discussion of the monitor object pattern, this is applied in lots of places in many pieces of software. It's applied in the Java platform. It's applied in the Android platform. And it's used to enable concurrent access by multiple threads to coordinate their activity. As you'll see, the blocking queues, the blocking decks, the thread pool executor, the async tasks, these are all examples of things in Android and the Java platform that use this pattern. And as a general rule of thumb, the Java util concurrent classes are used quite more frequently in Android than the low-level built-in Java monitor objects. And that's pretty consistent in modern implementations of things that use Java. They've given up, for the most part, on using built-in monitor objects. And that's because the classes in Java util concurrent provide so much more flexibility and so many more capabilities. Okay, so that's the end of our discussion of monitor object. So at this point, you should have a very good understanding of what the pattern does, as well as knowing in detail a way in which it's implemented in the context of the Java linked blocking queue, and then at least be familiar with the fact that Android uses linked blocking queue in various places in order to implement some of its own apps.